Welcome to the next video in the group theory series. In this video, we generalize what we discussed about D6. This next step could be to discuss the symmetries of a square. Again, we can label the vertices A, B, C, D counterclockwise around the square. The smallest rotation is a 90-degree rotation, sending A to B, B to C, C to D, and D to A. By repeated rotating in increments of 90 degrees, we get rotations r squared, r cubed, and r to the 0, which we also call just or write as the numeral 1. We again get reflections. In total, we get 4 reflections. However, in the triangle case, every reflection ran through a vertex and midpoint of the opposite edge. In the square, we get 2 kinds of reflections. So here you can see reflection with axis of symmetry running through vertices A and C, which leave A and C fixed and swap B and D. But also here you can see an axis of symmetry running through the midpoint of AD and the midpoint of BC, which swap AD and also swap BC. So those through 2 opposite vertices and those through 2 opposite midpoints. As before, we could name each reflection. However, it is nicer to merely pick one arbitrarily, call it S, and let it with R generate D8. So D8 is equal to 1r squared r cubed S rs r squared s r cubed s. And the viewer is invited to check that no matter which reflection is chosen here, the list of all these others generates all of the other reflections. The next obvious thing to do is to generalize to the case of any regular n-gon with n a natural number at least 3. We then get rotations 1r squared and so on up to r to the n minus 1. And reflections S, R, S, and so on up to R to the n minus 1 S. Since there are 2n elements in total, the set and group of symmetries is denoted by D sub 2n with all of these elements. This is called the dihedral group on a regular n-gon, and n-gon, just recall, is a polygon with n vertices. In this general setting, there are a few important facts that aid in calculation. One is that R inverse is R to the n minus 1 for any n. This is because R times R to the n minus 1 is equal to 1, which is fairly easy to demonstrate to yourself. The other is RS equals SR inverse. This is harder to prove, so let's first establish a lemma which will help to simplify the proof. If AI, AJ are adjacent vertices of the n-gon, then sigma AI, sigma AJ determine each sigma in D sub 2n. So in this diagram, you can see sort of a demonstration of the principle. If you look first at the blue arrows going from A to C and B to D, So C is sigma A, D is sigma B. Because this preserves orientation, it must be a rotation, right? Preserving orientation means that uh, A came sort of clockwise to B, and sigma A is also clockwise to sigma B. So that's right, they're kind of like relatively in the same ordering, so to speak, around the square counterclockwise. So that's preserving orientation. And any rotation always preserves orientation. Uh, then, because A rotates through 180 degrees, the symmetry must be R squared, the rotation by 180 degrees. Now, also look at this other demonstration of the same principle, but this time we'll imagine that A maps to itself, right? So sigma A is A. And also let's imagine that B maps to D so that sigma B is D. Now the orientation has been reversed, so we know it must be a reflection. And since A is fixed, then it's a reflection with axis that passes through A. The more rigorous statement of this idea is that if AI, AJ are adjacent vertices and sigma tau two symmetries of the regular n-gon, then if sigma AI equals tau AI and sigma AJ equals tau AJ, then we must have sigma equal to tau. That is to say, there is only one symmetry which does what sigma does to AIAJ, and likewise for tau. We will now use this principle to prove that RS equals SR inverse by taking RS to be sigma in that principle and tau to be SR inverse in that principle. We will in particular show that RS maps A1 to the same thing that SR inverse maps A1 to. And we will also show that RS maps A2 to the same thing that SR inverse maps A2 to. In this diagram, it's a little cluttered, but you can see basically the argument that we're going to first compute RS inverse, and we're going to assume throughout that the axis of symmetry S passes through A1. It's a simplifying assumption, and through either relabeling some of the vertices or perhaps by slightly adjusting the argument, you can make this basic argument work with minor adaptations to other cases. But this is the sort of core of the argument. So with this assumption, we will compute what RS does to A1. Well, certainly S leaves A1 fixed. And then we pass A1 into R, which sends A1 to A2. So at the end of the day, RS sends A1 to A2. We also check what SR inverse does to A1. Well, that's first going to map A1 clockwise, right? So another thing about R inverse is that you can either see it as R to the n minus 1, or it's the same thing as just doing a clockwise rotation by the smallest angle. And so that would send A1 down to AN minus 1. Then passing that into S would send it back up to A2. And so at the end of the day, we see that SR inverse does the same thing. It sends A1 to A2. Next, we check what RS does to A2. It sends it to A1. How do we know? Well, if you start from A2 and go to, or apply the reflection, then we come down to AN minus 1, and then R sends an minus 1 to a1. So ultimately, the symmetry RS sends a2 to a1. Then we check SR inverse and see what it does to a2. R inverse sends a2 to a1, and then S leaves a1 fixed. So it does the same thing. It sends a2 to a1. We have now checked that these two symmetries do the same thing to these two adjacent vertices and therefore must be the same symmetry. So we have now proved that RS equals SR inverse. By the way, right, that's one useful way of seeing what this thing is, but it's also worth, getting this slightly different version, which is that through just a little bit of multiplying by inverses and so on, you can see also that SR equals R inverse S. So one way to think about what all is going on here is that sort of algebraically, we're saying that you can move R from one side of S to the other in either direction. You just have to take its inverse when it arrives at the other side. The above, right, as I've already sort of pointed out, but I'll say here again, the above assume that S had an axis of symmetry running through A1. It is very easy to adapt this proof to all the other possibilities. One should note that the above now allows us to write every symmetry as R to the I, S to the A for an I between 0 and n, of course, an integer, and A in the set 0, 1, right? So A could be either 0 or 1. Let's just see this in action. So for instance, let's say that we take D12, which has n equal to 6. We can then compute the product of these two reflections. Notice that we would typically represent this reflection as R squared S. That's one of the reflections. And also we have another reflection, R cubed S, and we will often want to know what their product is. And what that means is that we would like to have it represented as R to the I, S to the A, right? Because that's how we try to kind of represent every object in D sub 2n. So how do we do it? Well, we use what we just proved, right? It tells us that we can move R across S if we take its inverse. So let's go ahead and split off one of these R's and move it to the other side of this S. I'm going to move my R's to the left. So that means that this goes down by 1 because basically I've split off one factor of R. And on the other side of S, it becomes R inverse. I could do it again, right? So split off one more R, and again, it becomes R inverse on the other side of S. Then do it one more time. And you can see that here, right, by the time I've put the two S's together, they cancel with each other because we know that any reflection times itself is the identity. So we might as well basically cancel them out. Here I have two inverses and R squared, so I might as well cancel them out as well. And what I'm left with is R inverse. Well, now it would be nice if I use this principle that R inverse is R to the n minus 1. Here n is equal to 6. So we get R to the 5. Because we maybe, just for the sake of expressing this exactly as I've written it earlier, reintroduce the S, but we would call it S to the 0, which we essentially just take to mean the identity.